With respect to who? With respect to the positive x-axis. So starting from there, this is x suffix s. This angle here, of course exaggerated, has to be much closer to the y-axis. This is 87 degrees. Once I have that, the next axis that is orthogonal to it is going to be ys, and that's going to be this direction here. Okay, so that's going to be perpendicular to axis. Does this make sense to you? Then I'm going to clear up this particular panel. Draw the rectangle. When I'm drawing the rectangle, my xs is going to be starting from the center, and ys is going to be this way. And now look at the value of the maximum in-plane shear stress that you're reaching from the reference line. Is it positive tau max in plane or negative tau max in plane? Starting from the reference line, the first shear stress value that I reach in this particular problem is negative tau max in plane. Which means, if you come and look at the side that contains the positive xs direction, what has to be the direction of the shear stress on there? It has to be pointing down. Does this make sense to everybody? According to the sign convention for stress, for shear stress. If the shear stress is positive, that means on the side where the area normal is positive, the shear stress has to be pointing in the positive y direction. That is not the case here, because I am seeing that as I reach from the reference line all the way to the first shear stress value, it is negative, which means that it has to be opposite to the sign convention. And I get one of these creatures, I'm pretty much good to go, because the rest of them follow suit. So this is going to be up this way and this way. And why I am saying this is because this labeling of the axis is completely arbitrary. Once I have this axis drawn, I can just throw it out of the window, because all it matters to me is what is the direction of the shear stress on these four faces, and how is the element rotated with respect to my original direction. That's all I care about. I don't care about the labeling of these axes. In your textbook they'll be called by a different name, x prime and y prime. Your textbook might actually draw them out this way. This would be x prime, and this would be y prime in your textbook. It's all the same thing. What matters? On this rectangular element, the direction of the shear stress is going to be the same whether I draw it, whether the textbook draws it, or auto mode draws it. Cannot change. Okay? I want to see if there are any questions, and I am not completed with this yet. I have the average stresses on all the faces. Sigma average, this is tau max in plane. Sigma average. On all the faces, you're going to have the average normal stress. And sigma average. Now, if you want, you can mark the angle. Not drawn to scale, of course, but it's supposed to be 87 degrees. Question before we proceed next to the strains. Two hands, yes, first time.
So, even if like our point was somewhere where we would hit the bottom of the y-axis, can we still find 2J to S1 either way? Like,
Alright, so okay, good question. So let's say that you're here, right? So now what you do is, from the reference line, the first shear stress value that you reach is your 2 theta S1. That's always the case. The first stress value that you reach from the reference line. As you see, in our problem, this was the reference line. As I go counterclockwise, what is the first shear stress value that I reach? I reach that minus tau max in plane. If my line were somewhere else, notice that my theta P1 would still be this way. Suppose this were my reference. My 2 theta P1 would still be starting from the reference counterclockwise all the way to the sigma 1 value. That will not change, if that is indeed the sigma 1 value. But for the shear stress, the first shear stress that you get, the maximum shear stress that you get, is going to be your culprit. Makes sense? You had a hand raised to one.
So, actually, off of this question now, so if the reference line, for example, was in the third quadrant and it hits, so if the reference line was in the negative tau max in plane, for example,
Yes.
so as it rotates clockwise and it hits the
Counterclockwise.
counterclockwise, I'm sorry. Once it hits the axis, would that be your sigma 1?
No. So that depends. So I guess the figure itself will be different in that case. Let me maybe get rid of this and then sketch it out. Okay? I'll sketch it out. So as an example. Let's say that this is plus sigma. This is plus tau. Let's say that my C was negative. C is somewhere here. And let's say that my A point was somewhere here. So this is C. This is A. I have to draw the circle. Okay. The largest positive value where it intersects is here. That's always going to be sigma 1. Sigma 1 is the largest of the principal stresses. So, for example, if this was, I'm also going to get rid of this figure if it's okay with everybody.
Did you say the largest positive value?
Largest
For
value,
sigma 1.
largest value in sign. So I'll draw one more circle and show you. These are all good questions, and you know, with the more problems we get to understand them, but you see time is limited. Let me draw one more. Point C and point A. I'm going to draw something that's on the negative. Let's say this is point C and point A. Now, this is positive sigma. Positive tau. This is the origin. There are two values on the x-axis where the circle is intersecting, right? So there is one value here, and the other value there. Both of them are positive or negative? Both of them are negative. Which is the larger of the two? The larger of the two is going to be the one that is the least negative. So that guy is your sigma 1. Okay, so this is now going to be sigma 1. This is sigma 2. In this case, this was sigma 1. This would be sigma 2. If I'm trying to find 2 theta P1, it's going to be the following. And of course, I'm going to have my plus tau max in plane, minus tau max in plane. They don't change. Okay. So 2 theta P1 in this case is going to be that. What about 2 theta S1? Counterclockwise. Start from the reference line. The first shear stress value that you reach is your 2 theta S1. Likewise, if I look at it here, the first shear stress value that I reach is 2 theta S1. And 2 theta P1, likewise, is this way. Does this make sense to everybody? there is a derivation which says that tan 2 theta S1 is negative 1 by tan 2 theta P1. We don't go through that derivation. What we are doing here will give you the exact same result as you get in any textbook. This is easier to understand in a sense of drawing it out. Okay? So in this case, my sign convention dictates that the shear stress here will be positive. So when I draw out my coordinates, it's going to be positive on the face where I draw my XS direction. Okay? Question 2 hands. Okay. 3 hands. Okay. First, second, third.
So I also had a quick question regarding when we draw the orientation of the plane, right? For the 2 theta S1, we know it's one angle, so we know that we can always shift it by whatever that angle is from the x-axis. But in case when we're drawing the principal state of stress, since we have 2 angles, how do you know when to use one angle to shift it by, or when is it use 2 theta P1 or 2 theta P2?
2 theta P1 is the angle to the first principal direction. One. So usually here is what I do. I don't calculate 2 theta P2.
Yeah.
I calculate only 2 theta P1 because I know that if this is my x-axis and y-axis, and let's say that this is this once again gives me something less than 90 if I calculate theta P1, but this is going to be my one direction. I'm good to go because my 2 direction is going to be perpendicular to it.
So whenever we're drawing the principal state of stress, 2 theta P1 is sufficient to draw the entire orientation,
Right.
because you're just shifting from the x-axis by whatever that is.
Absolutely.
And then theta P2 or sigma 2 would just be the perpendicular one.
Absolutely.
Okay.
Absolutely. And so there are 2 other hands, but I want to point out one more thing, and maybe we will have to hit the screens on Wednesday. Can I erase this panel here for everybody? Okay. Let's see if this makes everything solidify. So let's say I have the following motion. This is my reference line. Okay? Draw my circle out. Of course, those are the diameter points. I'm just drawing something that's a little oblong. Okay? Now, this is sigma 1, right? Because that is the largest value there. Sigma 2 is the other value. There is actually a third value which is sigma 3, which is 0. Because there are 3 stresses, 3 planes, x, y, y, z, x, z. If you're doing a plane state of stress, the third principal stress value is 0. We're not going to talk about that. Now, if I have to calculate 2 theta P1, what do? From the reference line, all the way here is my 2 theta P. Which, if I reduce to theta P1, is going to be an angle greater than 90 degrees. Right? So, if I now draw out x and then y, theta P1 in this case is going to be giving me the location of the one direction, which means that the 2 direction is going to be perpendicular to that and coming out this way. So the orientation of the principal plane itself is given to me. The direction of the principal stresses, I know that this is tensile, that is compressive. So if I draw the rectangle out, this is going to be sigma 1 and sigma 2. Does this make sense to you?
How did you determine that they were sigma 2 was compressive and sigma 1 was tensile from the
Negative.
Okay.
Right, because this is the origin, right? That's positive sigma. This is negative sigma, so this is going to be negative sigma 2. So sigma 2, you see, is actually in the sense of what we typically call a sigma 1, right? It doesn't look like it's a typical sigma 2. But what's typical, what's not, is who knows. It has to depend on the orientation. You see that? And theta S1, so what's that 2 theta S1 here? So start from the reference line, counterclockwise to the first shear stress that you meet is 2 theta S1. Okay? And that's going to be an angle that is less than 90 degrees if I find theta S1, and likewise one can draw it out. Maybe I'll draw that out here. X-axis, y-axis, so my xs is going to be at an angle less than 90. So this is ys for me. If I now draw the rectangle out for that, this is going to be my rectangle. Okay? It is hitting the positive tau max value, which means that according to the sign convention on the face that I am interested in, this is going to be the direction of shear stress tau, which means on the opposite face and all that, I already have an idea of what's happening. And on top of that, I have a sigma average. Depending on whether sigma xx and yy are both negative, I can either have a compressive average stress or a tensile average stress. That's completely numerically determined. If you know sigma xx and sigma yy, you're good to go. Alright, so my plan was to look at strains as well. I'm going to write down the following equations so that you can use them for your homework. We're going to come back on Wednesday and then look at them and then solve a problem using them. Okay? And I think by the looks of it, I want to spend most of my review session on Mohr circle. Drawing out Mohr circle for different states of stresses and then figuring out how to draw the orientation of the planes. And if there are any other questions, we can have them there. So bear with me for one last minute. Okay, so these are the equations that you need for stress strain. So this is for a three-dimensional state of stress-strain relations. Epsilon xx, your good friend Young's modulus 1 by E, sigma xx minus Poisson's ratio, nu, times sigma yy sigma zz. And the reason for it being, a stress in the x direction causes a strain in the x direction, but a stress in the y and the z causes a reductive strain in the x direction. And I'm going to go over this in much more detail in the next class. And likewise for sigma yy, 1 by E, sigma yy minus nu times xx plus zz. Epsilon zz is 1 by E, sigma zz, nu times xx plus yy. The shear strains, they are all unrelated to each other, so gamma xy is caused only by tau xy. Does not affect gamma xz or yz. I'm going to have gamma xy is tau xy by the modulus of rigidity g, gamma xz tau xz by g, gamma yz is tau yz by g. For your homework, use the values of, I'll give you the values of Young's modulus and Poisson's ratio, because I did not specify it in the homework problem, I think. So I'll specify those values after I go back to my office today. Okay? But if I know sigma xx and sigma yy and sigma zz, I can write out epsilon xx, yy and zz, and likewise for the rest of them. Okay? Thank you for your patience. As you see, these problems take time to understand. This is not easy material at all, but we will try our best.